In this video, we will compare different graph neural network architectures. The general idea is always the same. We start with a graph, pass it through a GNN encoder, and obtain node embeddings. These embeddings are vector representations of the nodes, and they should contain useful information about both the node itself and its surrounding graph structure. The important difference between GNN architectures is how they pass messages between neighboring nodes. In other words, each architecture defines a different rule for how a node collects, combines, and transforms information from its neighbors. Here, we will look at 6 common choices: graph convolutional network, graph isomorphism network, efficient graph convolution, principal neighborhood aggregation, graph attention network, and graph attention network version 2. The goal is not only to memorize their names, but to understand how each architecture preserves and passes the information. Most graph neural networks can be understood through the same basic framework: message passing. On the left, the yellow node is the node we want to update. We call it node I. The blue nodes around it are its neighbors. The yellow arrows show that information flows from the neighbors into node I. The first step is the message step. For every edge from a neighbor j to node I, we compute a message, mij, at layer k. This message can depend on the current embedding of node I, the current embedding of node j, and sometimes also edge features, eij. The second step is aggregation. Node I receives many messages, one from each neighbor. The aggregation function combines all these messages into one neighborhood summary, mi. This could be a sum, a mean, a max, a tension-weighted sum, or something more complex. The third step is the update. Now node I updates its own representation. The new embedding hi at layer k plus 1 is computed from the old embedding hi and the aggregated message mi. This 3-step structure is the common language behind most GNNs. The architectures we compare next mainly differ in how they define the message, the aggregation, and the update. The first architecture is GCN, which stands for Graph Convolutional Network. The main idea of GCN is normalized neighborhood averaging. On the left, the yellow node is the node we want to update. The blue nodes are its neighbors. The yellow arrows show that neighbor information flows into the center node. In the middle, the blue feature vectors represent the embeddings of neighboring nodes. GCN does not simply copy one neighbor. Instead, it combines the neighboring features using a normalized average. The word normalized is important. Some nodes have many neighbors, while others have only a few. Without normalization, high-degree nodes could produce much larger values just because they have more neighbors. Degree normalization keeps the scale more stable. After this normalized average, we get the new representation of node I at the next layer, written as hi at layer k plus 1. The formula shows the same idea in matrix form. H at layer k contains all node embeddings before the update. W at layer k is a learnable weight matrix that transforms the node features. A with a tilde is the adjacency matrix with self-loops added, so every node also keeps its own information. D with a tilde is the corresponding degree matrix. The expression D inverse 1/2, A tilde, D inverse 1/2 is the symmetric degree normalization. It tells us how strongly information should be mixed between connected nodes. Finally, sigma is a nonlinear activation function. So the intuition is simple. GCN lets each node update itself by taking a stable, normalized mixture of its own features and its neighbors' features. This makes GCN simple, efficient, and stable. But because the aggregation is mostly averaging, it treats neighbors in a very similar way. Next is GIN, which stands for Graph Isomorphism Network. GIN was designed to preserve graph structure more strongly than simple averaging methods. On the left, the yellow node is again the node we want to update. The blue nodes are its neighbors, and the arrows show that their information is sent to the center node. The key difference is in the aggregation step. GCN uses a normalized average, but GIN uses a sum. In the middle, the blue bars represent neighbor embeddings. These embeddings are first summed. Then the summed neighborhood information is passed through an MLP. This is important because summation preserves more information about how many neighbors contribute to the representation. For example, if two neighborhoods have similar average features, an averaging method may map them to similar representations. But if one neighborhood has more nodes than the other, the sum can still capture that difference. The formula shows the GIN update. hi at layer k+1 is the new embedding of node I. The MLP is the learnable neural network that transforms the aggregated information. Inside the brackets, we have two parts. The first part is 1 plus epsilon multiplied by hi at layer k. This keeps the node's own previous embedding, and epsilon controls how strongly the self-information is weighted. The second part is the sum over all neighbors j of node I. This adds the embeddings of the neighboring nodes. So the intuition is GIN keeps the node's own information, sums all neighbor information, and then lets an MLP transform the result. Compared to GCN, GIN is usually more expressive for structural differences because it does not collapse neighborhoods only through averaging. Next is EGConv, which stands for Efficient Graph Convolution. The main idea is that one aggregation function may not capture everything about a neighborhood. On the left, the yellow node again receives information from its blue neighbors. But instead of using only one aggregation rule, EGConv looks at the same neighborhood from several different views. In the middle, the blue feature bars are the neighbor embeddings. These embeddings are passed into different aggregators, for example, mean, max, and sum. Mean captures the average behavior of the neighborhood. Max captures the strongest feature response. Sum keeps more information about the total amount of neighbor information. These different aggregation results are then sent into the fusion block. The fusion block combines them into one updated node representation. The output on the right is the new embedding of node I at the next layer. The formula describes this more generally. X prime I is the updated feature of node I. Concat over H from 1 to H means that EGConv can use multiple heads and then concatenate the results. The set A contains the aggregation functions, for example, mean, max, and sum. The index B runs over basis weight matrices. Instead of learning a completely separate weight matrix for every case, EGConv uses basis transformations, W sub B. The term W sub B xj means that the neighbor feature xj is first transformed by one of these basis matrices. The aggregation symbol combines the transformed features over all neighbors of node I, including node I itself. The coefficient W sub IH aggregation B is an adaptive weight. It tells the model how strongly a certain aggregation type and basis transformation should contribute for this node and head. So the intuition is EGConv creates several neighborhood summaries and learns how to combine them efficiently. Compared to GCN, it is more flexible because it does not rely on only one normalized average. Next is PNA, which stands for Principal Neighborhood Aggregation. PNA builds on the idea that one aggregation function is usually not enough. On the left, we again have the yellow center node and its blue neighbors. The label di equals 4 means that this node has degree 4, so it has 4 neighbors. This degree information is important in PNA. In the middle, the blue bars represent neighbor embeddings. PNA first applies several aggregators to these neighbor embeddings. For example, mean captures the average neighborhood behavior. Max captures the strongest signal. Min captures the weakest signal. Standard deviation captures how much variation there is inside the neighborhood. So instead of describing the neighborhood with only one summary, PNA describes it with several statistics. But PNA adds one more idea: degree-based scalars. A node with 2 neighbors and a node with 50 neighbors should not always be treated in the same way. The scale of the neighborhood matters. Degree scalars use the node degree to adjust the aggregated messages. The aggregator outputs and the degree-scaled versions are then combined, and the result becomes the updated embedding of node I. The formula shows this idea. Mi at layer k is the combined neighborhood message for node I. Concat means that we concatenate several combinations together. The symbol A belongs to the set A. This represents the different aggregators, such as mean, max, min, and standard deviation. The symbol S belongs to the set S. This represents the degree scalars. The term A sub I of the neighbor set means apply one aggregation function to the embeddings of all neighbors of node I. Then S of D sub I rescales this result based on the degree of node I. Finally, the second formula says that the new embedding H sub I at layer k+1 is produced by an MLP using the old embedding H sub I and the combined message M sub I. So the intuition is PNA creates a richer neighborhood description by combining multiple statistics and adjusting them with degree information. This makes PNA more expressive than simple averaging, especially when graphs contain nodes with very different numbers of neighbors. Next is GAT, which stands for Graph Attention Network. The main idea of GAT is that not every neighbor should contribute equally. On the left, the yellow node is the node we want to update, and the blue nodes are its neighbors. The lines going into the yellow node represent attention weights. The yellow lines mean larger attention weights. These neighbors are considered more important, so they influence the update more strongly. In the middle, we take the representation of node I and the representation of one neighbor, J. GAT uses these two representations to compute an attention score. This attention score tells us how important neighbor J is for updating node I. After computing scores for all neighbors, GAT applies a softmax. This converts the raw scores into normalized attention weights alpha ij. Then, the weighted sum block combines the neighbor features. Instead of a simple average, each neighbor feature is multiplied by its attention weight. The output on the right is the updated embedding of node I. The first formula shows how the raw attention score, EIJ, is computed. WHI is the transformed feature of node I, and WHJ is the transformed feature of neighbor J. The bracket means that these two transformed vectors are concatenated. The vector A is a learnable attention vector. It maps the concatenated features to a scalar score. Leaky ReLU adds a nonlinear activation to this score. The second formula first turns EIJ into alpha ij using a softmax over the neighbors, J. Then the new representation H'I is computed as a weighted sum. Each transformed neighbor feature, WHJ, is multiplied by its attention weight alpha ij. So the intuition is GAT learns which neighbors matter more and then uses these learned weights to build the next node embedding. Compared to GCN, GAT does not treat all neighbors similarly. It can focus more on the most relevant neighbors. Next is GATv2, which is a more flexible version of the graph attention network. The main idea is still attention. On the left, the yellow node is the node we want to update, and the blue nodes are its neighbors. Just like in GAT, the yellow lines represent larger attention weights, so some neighbors influence the center node more strongly than others. The difference is not that GATv2 removes attention. The difference is how the attention score is computed. In the middle, we take the representation of node I and the representation of neighbor J. These two representations are passed through a joint transform. This is the key idea of the architecture. GATv2 first considers the pair of nodes together and then computes the attention score. After the joint transform, the attention score block produces a raw score. This score is then converted into the attention coefficient alpha ij. The small comparison text says the same thing. In the original GAT, the features are transformed first and then scored. In GATv2, the score is computed after a joint transformation of the node pair. Now let us look at the formula. EIJ is the raw attention score between node I and neighbor J. The vector A is a learnable attention vector. Inside the leaky ReLU, we have W applied to the concatenation of HI and HJ. This means the two node representations are first put together and then transformed jointly. This is the central difference compared to the original GAT. Then alpha ij is computed using a softmax over all neighbors J. The softmax converts raw scores into normalized attention weights. Finally, H'I is computed as a weighted sum of transformed neighbor features. Each neighbor feature WHJ is multiplied by its attention weight alpha ij. So the intuition is, GATv2 still learns which neighbors matter, but it uses a more flexible scoring function to decide this importance. In short, GAT learns attention weights. GATv2 improves how these attention weights are computed. Now we can compare the architectures side by side. The circles are a compact way to show tendencies. An empty circle means low, a half-filled circle means medium, and a full circle means high. These are not absolute scores. They are meant to show the main trade-offs between the architectures. GCN is the simplest architecture in this comparison. It is easy to understand, efficient, and stable, but it has low structural detail because it mainly averages neighbor information. GIN is less simple than GCN, but it is much stronger in structural detail. The reason is that GIN uses some aggregation and an MLP, which helps preserve differences that averaging may remove. EGConv has medium simplicity and uses strong multi-aggregation. It combines different aggregation views, such as mean, max, and sum, but it does not explicitly use degree scalars or attention. PNA is the richest aggregation-based architecture here. It uses multiple aggregators and degree awareness. This makes it expressive, but also less simple. GAT and GATv2 are strongest in the attention column. Their main advantage is that they learn which neighbors should matter more. GATv2 has a similar high-level profile to GAT, but its attention scoring function is more flexible. So the main message is, there is no universally best GNN encoder. The right choice depends on the graph, the task, and whether you need simplicity, structural expressiveness, rich aggregation, degree awareness, or attention. So to wrap up, all of these architectures follow the same general message passing idea. GCN, GIN, EGConv, PNA, GAT, and GATv2 all update nodes by using information from their neighbors. But they differ in how this neighbor information is aggregated. Some architectures focus on simplicity, some focus on structural detail, some combine multiple aggregation statistics, and others learn attention weights. This is why the encoder choice matters. It changes what kind of graph information the model can preserve and use. Thanks for watching, and see you in the next one.